Hi everyone. So I'm Philippe Bacon. I'm here at the EPC. I'm glad to be here among you to talk to you about denoising gravitational wave signals with VAs. So I'm working with Mihai and Agatha. So what this presentation is about, we are trying to denoise gravitational waves. So gravitational waves injected signals such as the one in blue into real O1 interferometric data in yellow. So I've been preparing an audio sample to make you have a taste of what we are able to do. So what you're about to hear is 3 times the noisy signal. Okay, let's hope it works. Nope. Okay, this was short, but you may have heard the chirp because it's quite loud in this audio. So maybe again. Okay. And denoised, it gives this. Nice. Okay. I'm going to go through a bit of context again, sorry. So actual gravitational waves, models such as are mostly such as for model for compact binaries are relying on Gaussian noise hypothesis. But we do know that there is a non-Gaussianity lying in the detector data. It's important to deal with it. Again, low latency searches are also very important as we expect more and more detection in the future. The instrument gain in sensitivity so that we can share the alerts among astronomers. And the models we have for model-based searches are optimal. However, there's not the parameter space of those systems we are targeting are not fully covered. I mean, for example, eccentricity or precision. And machine learning can help us have a taste of, can maybe learn what we incorrectly assume in these models. So for all this reason, deep learning is interesting. So the Bayesian aspect comes after. So the novel approach we propose roughly. So the recent application of deep learning involves classifiers. We opted for the regression addressing the regression problem, more specifically denoising. A rule of thumb that exists in the community is that when you have time series, most of the time, well, it actually is not justified here from the talk I've seen. You treat time series with recurrent networks, and you use convolutional networks for images. And here we're using a 1D convolutional network to perform on the time series that are given by the instruments. And again, you're all convinced about these points. Point estimate is useless, and we need Bayesian inference on top of the classical deep learning. Okay. So the architecture of autoencoder. So you have the inputs, so the encoder, the bottleneck, and the decoder. But the key to deal with noise is sparsity. Sparsity is a key concept when you want to design an algorithm which is robust to noise. And this is why the autoencoders is very good at, can be very good at denoising, because it enforces your high-dimensional input gravitational wave to live in a low dimension. You're compressing the information. And this is the architecture, the structure of the network that enforces this sparsity criterion. For sparsity enforce, to have few high coefficients in your representation. For instance, if you have a sinusoid on top of which you add some Gaussian noise signal, if you map this signal into the Fourier domain, then you will have basically a peak. So you will have a very, very bright single pixel that describes most of your signal. And this is a feeling about sparsity. So on top of this DAE, we introduced some Bayesian framework, and we arrived to VAE. So this is another representation among the ones you have seen today. So in green, you have the encoder, a latent space, so the bottleneck is in red, and in blue is the decoder. So you have two distributions you're learning, and during the training of this network, you are trying to make x and x prime as close as possible. So you're doing it by minimizing the loss function, which is function of these two probability distribution you're trying to learn. The encoder, which tries to enforce a regularization term, that means to incorporate the prior, which for some reason is a unit normal. It has to deal with the reparamerization trick Tom evoked this morning. And the decoder, which is the reconstruction term, and that enforces the network to denoise your signal. And you also see, and this is important, this is a bit more than a VAE, it's a beta VAE, because you have this beta term in the loss function. I'll come back to that later. About the data set, so we have a bank of gravitational wave signals with a f low, which is 30 hertz, which corresponds to the lower frequency limit of the LIGO instrument. We simulate binaries with the individual masses sit in the 10-30 solar masses range, and the signal-to-noise ratio is between 5 to 20. For the O1 run, the limit of the detectability being around SNR 7 or 8. Okay. So as stressed before, the input of our VAE is a corrupted version of the gravitational wave signal. So the White-tone gravitational wave signal plus real O1 noise, and we try to recover the White-tone gravitational wave signal. About the training, it's better than usual. We've been training it on 3 chunks of 1,000 waveforms each, and we added on top of this a flat signal probability. This means it lets the user tune what fraction of the training set is replaced with flat signal. We think this is important to make the network robust to Gaussian noise. If you do have a gravitational wave signal in your data, then you should expect your VAE to output reconstruction that looks like a gravitational wave event. But if there's not, then you should expect your VAE to have a flat signal in the output. We did all we can to prevent overfitting by reducing low learning rates, and we monitor the training and testing losses. The training time is about half a day on my laptop, so non-GPUs. And just for mentioning, we used for the prediction of the VAE, we're passing n times the noisy signal into the VAE to compute the mu in sigma. This is equivalent to outputting a probability. Said differently, if you have one gravitational wave signal plus noise, you pass it n times into the VAE, and it outputs n different realization of the signal, and then you make some statistics on it. You compute the mu and sigma. And this is equivalent to predicting distribution. we're not using TensorFlow probability, for instance, that fully can help in doing this properly. So this is the result we obtain. Okay, so there are plenty of signals I can detail. So it's just to mention SNR 17, so it's quite high, but a good example to begin with. The yellow signal is the relative interferometric noise plus the gravitational wave signal. In blue, you have the clean gravitational wave signal. In red, you have the mean estimate of the VAE, and the green region are the 2 and 3 sigma regions. Again, we will come back to this close to the end of this presentation. And second example on a fainter signal with SNR 10, you see that, so on the previous signal, you see that on the SNR 17, you see that the phase and the amplitude are very well recovered, and they are sitting in the error bars. While for fainter signals, the phase is also very well recovered, although we overestimating close to the merger. However, they're still within the error bars. Just to mention, this is a quite small network. It's about 340,000 trainable parameters. Our experience show that adopting a bigger one may cure this problem. So yeah, going back to the uncertainties, theory of VAE told you that what is provided by a VAE is simply the probability of the data, knowing the latent representation you have, the sparse representation you have of the bottleneck. But it leads to the following remark in the context of denoising. I remember the input on the VAE is a corrupted input. So the latent representation you have of the bottleneck is actually Z noisy, and not, strictly speaking, Z. Then the decoder tries to reconstruct the waveform from this corrupted signal. That's why it's important to deal with sparsity, so as to enforce Z to be as close as possible from Z noisy. And last point, which is very important for the future of our project, the VAE loss function suggests that the uncertainty is driven by the beta parameters. Actually, that's why our most recent test suggests, and actually we're also here to discuss this point. Our interpretation about this is the following. In the SNR 17 example I've been showing, the probability that the true signal lies in the 2 sigma credible region is only 50%. I would naively expect that the signal to be present, well, according to the well-known rule in statistics, to be present 95% of the time. And respectively, for this 3 sigma region, I would expect this true signal to be present more than 99% of the time. I'm not sure, actually we're not sure about this interpretation, and we hope for making the beta parameters to be trainable, as this is the point we want to solve in the future. The beta parameters that I've been presenting is for the moment fixed, okay, and we're not training for it, and this is a margin of improvement. And I did this slide this morning because I found this roundtable was very, very useful in terms of interpreting what's giving the VAE, what is the probability given by a VAE. So it's been said that the VI in general may not suit every use, in the sense that the posterior, you have nothing that tells you that the posterior you have is effectively Gaussian. In our case, it's Gaussian. However, I've been saying the green posterior we have is very narrow around the signal, so we have a little hope that our assumption that the Gaussian posterior is quite reasonable. If it were like a very if it were very spread around the signal, then it could have been a clue that we were doing something wrong. But here, maybe it goes well. Also, another remark: the flat signal probability we are adding in the training can actually depopulate some part of the parameter space we're probing with the training set. This means that, at the light of what has been said this morning, we are increasing the aliteratic uncertainty. This is to be discussed, and we look very happy, and we are looking forward to going to the TensorFlow probability session to learn more and hopefully get better insights about the probability we're having with our beta VA. So I can let you with a conclusion. So we've been using convolutional layers to solve a regression problem. I mean, this is quite successful. The VAE is an elegant framework to address the denoising problem and to have a sense of these uncertainties, although it is not clear yet. And we are margin for improvement to make beta trainable and helps in interpreting the probabilities. That's it for me.
Questions for Philippe?
On the error bars that you're showing, is it just the sigma at the output of the model, or it's sampled from your your latent space posterior and then samples from?
No, it's just the output. It means to compute these green regions, I've been showing the VAE n times the same corrupted signal, and the outputs I have some n different realizations, and then I'm
Okay.
No second.
Okay, thank you.
Maybe a first quick question. The reason why you don't train beta is the technical question, or is it technical reason, sorry, or is it?
Yeah, mostly. So basically, we're not using TensorFlow to do it, but I already know. I've seen some examples of tutorials that show that you can train a beta, and it's mostly for technical reasons. But hopefully tomorrow morning I'll be able to train it.
Yeah. So maybe then quick question. So what exactly do you see your algorithm used for in the gravitational wave community?
Okay. Yeah. So first of all, for the moment, the primary application of our algorithm would be as a pre-processing. Typically, you have the HFT coming out of your interferometer, then you whiten it, you denoise it, and then you can pass it to actual gravitational wave searches like model or unmodeled searches that exist in LIGO-Virgo collaboration. I mean, this is as a pre-processing step, this is the best information you can give to those who come after.
All right. Any other questions? Well, let's thank Philippe again.